Alright, so let's start with solving this textbook problem 49 in chapter 19. So we'll start with drawing a diagram. So the first thing it says is 2 moles of sample N2 gas at 0 degrees. So before we move on, let's just draw that. So there's a sample gas, number of moles is 2, and it's a sample of N2 gas. We can label that if we want at 0 degrees. So temperature is 0 degrees Celsius, heated to 150 degrees Celsius at constant pressure. So this is going to, we'll draw a before and after diagram. Any changes in the situation encapsulate all the information. It says at constant pressure. Okay, so since the pressure remains at 1 atm, so we'll write that down. Determine the change in internal energy. So this sounds like it's asking for the aim now, so we'll write down aim. And so first we want to find the change in internal energy equals question mark. And the second thing it asks for is the work the gas does. So it's the amount of work that the gas does. So it's the work done by gas. So it's important to label this. This label will tell me whether it is positive sign or a negative sign later. Okay, and finally the heat added to it. So C, the amount of heat added to gas. Close question mark. Okay, so sorry, I should have finished this part. It's heated to 150 degrees Celsius. So now I have two variables that I'm repeating, so I should distinguish them by labeling T initial and T final. Alright, so now we have every information we need. We're ready to focus on the problem to solve it. So the first thing is we want to find the change in internal energy. Right? So we want to think about all the relevant formulas that is useful. The first thing that comes to mind probably is the first law, right? So this is the first law of thermodynamics. Remember, what you want to do is think about any relevant equations or definitions that you can use. Okay. Another thing that I might want to transcribe before we move on is isobaric, which means also the pressure, which should also give you two related formulas. For example, immediately, the change in pressure is 0, or pressure is constant, right? And as a result, you should also remember in that scenario, P is constant. You can pull that out of the integral of the definition of work done, giving you a very simple formula for work. Okay. All right, so we'll start with, so changing internal energy. Another formula that's useful is 3/2 nRT. That's any ideal gas. That's basically from the ideal gas law. Any ideal gas follows this kinematic formula. So now which equation here might be most useful, because I don't have Q and W, so probably this one is the most useful for solving part A because I'm given T, and that's a good start, right? So we'll write down change in internal energy is the change, well, internal energy is 3/2 nRT, so change of it is change of 3/2 nRT. Whenever you see something like that, whenever you see something like a change, pull out any constants, so it's 3/2. N, R, these don't change. N particularly shouldn't change, the number of moles, unless the gas leaks out of the box, but since the question does not say anything about that, we can assume there's no leakage, so the number of moles is the same, and it's just change in temperature. So now that you're down to this line, you want to try to simplify the problem, and the way to go about that, as we discussed, is that you can check off everything that you know and anything that you don't know and see if you get anything closer to the answer. So first, N, I do. It's 2. R is the universal gas constant. I do know that. And change in temperature, I do know that as well. All right, so all that's left to do is plug in the numbers. That's 3/2, and R is 8.31 in SI base units. Change in temperature, technically everything should go in SI base units into my formulas, which is Kelvin. However, the difference in Celsius and the difference in Kelvin is the same. So I can just put in 150 minus 0. Right? So all that's left is to plug in the calculator, which I'll do very quickly here. And that gives me 3,739.5. which we want to round it to a decent significant figures, which should be around 2 significant figures from the numbers that are given in the problem. We can double check if we want. So if I just double check, I see that actually everything seems to be given in 3 significant figures. So let's go with that. So 3 significant figures, which means it's 3,740. And all that's left to do is to put in the SI base units for energy, which is joules, and we're done. So that's part A. Yeah. Okay, moving on to part B. Then we want to find the amount of work done by the gas, right? So as we see, you have two options. You can go with this formula or this formula, and looks like this seems to be the most promising of the two because we don't have the amount of heat added, and that seems to be part C. So we'll go with the second one. So I'll do change in work is P delta V. The pressure is constant, so that is immediately known. How about the volume? The volume is not given. However, this is a chance where you can think about what are other relevant formulas that involve volume to some of the variables that are given. And ideal gas law is always a good bet when you see something like N and T and V. So let's see if we can apply ideal gas law to that. So any change in volume is is nk and nRT divided by P. So we can write that. Okay. All right. So now this looks like something very complicated. Remember, the trick is anytime you see a change like this, you see a delta, pull out things that are constants, and it will immediately make your life drastically easier, right? So P is a constant, N is a constant, R is a constant. The P's do cancel, leaving you with just delta T, and that gives you a very simple relationship like this. And now you can ask yourself, do I know everything? Give it a quick check. Yes, I do. Yes, I do. Yes, I do. And you're done. So let's quickly plug in the numbers, and we'll see what we get. Okay, so it looks like we got 2,493. Let's round that to the correct significant figures. That's 2,490. And let's put in the units, which is SI base units, which is joules. So actually, before I underline this, I should check if the sign is correct. So in this case, we want to find the work done by the gas. So we need to know if the volume is expanding or decreasing, because work done is about change in physical volume. If the gas is doing work by expanding the volume or decreasing the volume. So this we need to find out whether does this increases or decrease. That looks like it's directly related to if the temperature increases or decreases. So temperature increases over here, and in that case, it means the volume should increase according to this part of the analysis. Another way, a more intuitive, physical way to think about that is imagine you need to keep the pressure constant while you increase the temperature. Well, there's only P, V, and T, three variables going on. So if you're keeping the pressure constant and you're increasing the temperature, the only way to do that, because if you increase the temperature, naively pressure will increase as well because there's more kinetic energy in the particles, there's more bombardment to the walls of the gas, so the pressure of the walls on the walls should increase. However, if you need to maintain the pressure, the only way is to expand the volume a little bit. So volume should increase. Relying on intuition is great, but sometimes things can be a little bit confusing or it might be counterintuitive. It's good to have both the analytic double check as well, and that seems to confirm. So the work done on the gas should be positive. We can emphasize that. So the work done by the gas, so the gas is doing the work, it's expanding the volume. We can emphasize that by putting a positive sign there. Of course, that's not necessary, but just to include that we have made the discussion and we have thought that through just in case the next time it is asking for the work done by the environment or the work done on the gas. Okay, so that brings us to part C, which looks like there's only one relevant formula left, which is the first law, because we already know 2 out of 3 of those variables, so that seems like a good fit. So we can directly do that. So delta Q, or let's write that actually starting with this. And we should ask ourselves, should I plug in positive numbers or negative numbers in each case? So for the change in energy, the temperature increases, so the gas definitely increase in energy, so we should put in positive number over here. Delta Q is our variable, our unknown we want to solve. And how about the work? So the gas is doing the work over here. So if the gas is doing the work, the contribution to the internal energy would be negative because the gas, by doing work on the environment, it's losing energy in its system. So we should plug in the negative number over here. And that brings us to, meaning delta Q is 3740 plus 2490. And I'll quickly punch in the numbers. And that gives me 6,232. Round that to a rough significant figure. There are three significant figures, so that's 6,230. And the SI unit is joules. Okay. So we seem to be getting a positive sign here, which suggests we're adding heat to the system. And we can do a sanity check if that makes sense. And it should, because we are increasing the temperature. All right, so this is the problem. Hope you enjoyed that. Let's see you next time.